Here we go. Here we go. Making an estimate or decision making? Well, an estimate is something with a plus or minus, like an error. How many times have you done that, where you've gone out, collected some data, you've got an average, and then someone says, plus or minus what? Well, I'm going to show you how you get your plus and minus, in a very clear way. Decision making is slightly different. This is where you'll turn around and say, I'm going to compare what I got out there to some standard. And this is sort of like a comparison to an action level. Here we go. 20 samples. We want to know the average potassium level. They want us to be pretty sure of the result. So it's going to be plus or minus roughly 2 parts per million. We use a spreadsheet and we get the answer 45.69 with an error plus or minus 1.67. Straightforward? Sure. Oh, really? Now you start worrying. What kind of average? There's more than one average. There's medians and modes and means. Where did that 1.67 come from? I don't know, I just put it into the program and it told me. You're pretty sure. What do you mean you're pretty sure? Was this a random sample? Well, maybe to some folks this all makes sense, right? Now I'm going to point at Melinda. Right? Yeah, she turns around and says, what's the problem? But for you, who's got to explain this to management, there could well be a problem. Well, you see, the thing is this. Estimation involves intervals. Let me stop right now. When we do a poll to see whether people agree with President Trump's policies, they give you an answer with a plus or minus, don't they? At the very end, if there's enough time, I'll show you where they get that plus and minus from. It's a lot cuter than you think. So here we go. We can construct something called a confidence interval that deals with the mean and some error estimate. And when we say this, we say that our best guess is 25.7, but it could be between 23.7 to 27.7. All right? That's what we're saying. So we go to a textbook. Do you like that? No. It's all right, be honest. No, nobody really likes that. I mean, it's full of spiky things and alphas and things like that. Well, most of the time you actually want the first one. Most of the time you want this one. And look at what it's got. There's your average, the mean, plus or minus t. Yes, that's something you limeys like. Joke. T, right, with a whole lot of little flimsy bits. S is probably the standard deviation, and N is the actual number in your sample. So you say, all right, okay, fair enough. This is why I've given you the actual handouts, so you can actually say, oh, well, there it is. N minus 1 is the degrees of freedom for a t-test. Have you ever tried to explain to management what degrees of freedom are? The guy says, I don't know, is this sort of something that happens in prison camps? Yeah. And you say, no, it's something that statisticians bandy around. Well, most of the time, when you're dealing with one sample, it'll always be n minus 1. But there are exceptions, don't worry about it. And so the upper end of a confidence interval is called, logically, UCL, and the lower end is going to be LCL. So you can actually say there's an upper and a lower. All right, here's an example. We got 8 fish out of North Lake and had a mean weight of 84.3 grams with a standard deviation of 11.05. Can you calculate standard deviation? If somebody gave you the formula and a calculator Could you calculate the standard deviation of a set of numbers?
Yes.
Exactly. Because, obviously you've done that on, many occasions, all right? So yes, you can do that. Where do you think this came from? This is often called, very, very prosaically, T-tables. So where do you think you get them from?
The back of the book.
The back of the book, exactly true. 100% correct. Yeah, you get them from the back of the book. And there it is. Do your calculations, T times standard deviation divided by the square root of n. Straightforward? Yes. Now, what do you know then? Here's something that you must realize about confidence interval. It's a technique. It doesn't mean you have definitely captured the unknown answer. It just means you have a probability that you've done that. A large sample leads to a small confidence interval. Is that logical? Yeah, give me a huge big sample, I can be pretty accurate. Give me a small sample, I'm going to be everywhere. Large variability, less certainty. Could you do this? Could you do this? Can't hear anyone.
Yeah, I have a feeling you're going to make us do it.
In fact, your very fears in front of you. All right, here's some data, and I've done a cool thing. I've given you all different data. I've given you all different data, so it's no good looking over and seeing what they got. Depending on which data set you've got, someone's got sort of like F, someone's got G, there's a double C somewhere.
So everybody's got different data sets
So we've all got different data sets.
from this giant population that we sampled from.
I'd like you to look at this just for a moment. Here's the answers. First thing, does it look reasonable? Look at all the answers for a moment. Does it look reasonable, guys? First of all, should they all be the same? No, of course not, because you've got different random samples. So they can't all be the same. Do they look reasonable? And the answer is yes, they do. Yeah, they look very reasonable. And so actually, see, there's 60 different data sets. You've got one of them. And now you've got all the answers. Notice that all the intervals look reasonable. Now suppose I turn to you and I say, through a whole lot of completely exhaustive readings, I can tell you that the true mean, not your sample mean, you've got sample means, but the true average out there is actually 20. You've all got a different data set, and now I'm telling you that you've calculated your confidence interval. Now then, if I told you that the real answer was 20, look at the first data set. Did that first data set include 20? Yes, it did. Did data set B include 20? What about data set C? Who had C? There she is! Look at this. Data sets. If you've got C or Q or triple C, you actually missed.
What do you mean with the true value?
True value. Well, you see, okay, think of that as being a hazardous waste site. There's a true average amount of contamination out there. You take a sample and try and see what that sample average is going to tell you about the true unknown average. You'll never know the true unknown value. But here I'm telling you, supposing I know because I planted it. In other words, it was a controlled experiment. You didn't know that. But the true answer is 20.
Okay, and in sample C, none of the samples that were collected in that time frame included the true value.
Aha!
But
Yes.
there's a confidence value.
That's right. In other words, what's happened with the person that got data set C, by chance, had lower values in there than other people. Did she know that? No, she didn't. And so when she calculated her 95% confidence interval, she was 95% sure she had captured the true value. Did she? No. She did. He got it. And that's the whole thing about a confidence interval, is the fact that most of the time you're going to be right, because that's the way confidence interval works. Be aware that, that on occasion you'll miss it. So if you only do these a few times, do you think you'll usually be okay? Yeah. I mean, 95% chance of being right. If you were on the floor here, right, and let the pit manager know that you're going to be 95% right, what do you think the pit manager will do?
Wow.
Escort you from the building, yeah? No, because that is almost certainty, and they can't deal with it. How about decision making? Let's have a quick look at decision making. This is the Pourquoi site. There were 30 random samples. The mean of the samples was 374.131. I'm always pleased to see all those decimals. The health and safety standard is you've got to be less than or equal to 40 milligrams per kilogram. Does this look like you can use this information to make this conclusion that it's really less than 40? On the surface, does it look like that is well below that? It does, doesn't it? But what makes you a little bit uncertain? Well, there's a standard deviation going on here. In other words, there's values all over the place. The average of your sample seems to be less. But this is human habitation. Can you afford to make an error? These are human beings, all right? I mean, what do human beings do? They have kids. What do kids do? Play in the dirt, all right? And what do they do with the dirt? They eat it. Of course, I never did something like that. I was always a nice little lad. So look at this. Are we sure? Are we really sure? Well, we can set this up as what's called a test of hypothesis. And we actually use a very easy formula like this. It's called student's t-test. You'll see it often referred to that, and there's a long anecdotal story about why it's called that, but just allow it to be called a t-test, or if you hear it called student's t-test, same thing. There we put the values in. There we set up the rejection rule. If the t-value we get is less than the t from tables, then we're in business.
Why do you have minus t?
Because, you see, this is a minus. Because the way we set up the null hypothesis
It's more
is
extreme.
yes, exactly, more extreme. Well, as the calculated t is not less than the t from tables, and if you look up the t from tables, it's on the back of your thing there, you suddenly say, well, there's not overwhelming evidence that it's less than 400. On the surface, it seemed like the value that you got, 379, was indeed less than 400. I mean, you don't have to be a mathematician to work that out. The problem is, as random noise or random variables were going on here, you couldn't be absolutely sure that's what the test will do. Now, here's some questions for you to mull over. Where did this thing called null hypothesis come from? First of all, do you actually use the word null hypothesis in real life? This morning when you got up, did you say, oh, my null hypothesis for today? No, you didn't. No, you didn't. Yeah? Only weird people think of things in null hypothesis. Statisticians have no problem with it at all. But you're always worried about us lot anyway. Where did these T tables come from? Yeah, you showed me them, but are they readily available? Did you really get a random sample? There's a lot going on when you say take a random sample. Think of that lawn out there, guys. Think of that lawn out there. If you're going to take a random sample, wouldn't you sort of like go all over it? And if you were really desperate for a cup of coffee, would you just go out and go, oh, quick, he wants these real fast. I mean, there's a lot going on when you say, did you take a random sample? Be careful. There really is a lot going on. And what do you mean, overwhelming evidence? If the average was 374, why isn't it clean? Well, here you go. Here's how things are actually set up. In general, a hypothesis test has 5 steps. The first one is the null hypothesis. The second is the alternative. Third is the calculation. The fourth is the comparison to critical level. And then the fifth is the actual conclusion. And although we're going to deal with this in terms of a t-test, this setup applies to any statistical test. If you want to talk about Godzabala's test, it'll be exactly the same format. And that's very, very comforting because it means if they all got the same format, we know how to deal with it at each stage. Well, we're going to look at the one sample t-test, and what we're going to do is concentrate on this thing here. Look at that last bullet for me, guys. The one sample t-test, it's got limitations. If there's outliers, it's not very good. And of course, the first thing that you're going to say to me is, okay, so what do? What do? Come back this afternoon, I'll show you. So yeah, it's pretty robust. I mean, in other words, it's not so delicate that it falls apart as soon as things start to go wrong. It's good. It's really very good. All right, and that's why we use it so often. So let's have a look. Now then, first thing you say to me is, all right, okay, fine, I'm lost already. You know, where can I find out more about this? And the answer is, go and look in a standard textbook, right? And you make the mistake of doing that, and you suddenly realize that you just are a bit at sea. I mean, because all it does is it just goes zoop. It's like those brilliant people that are good with computers, and you say, I'm stuck on this, and they go, oh, it's easy, you just go, and you say, thank you very much, I enjoyed having you here for the microsecond, and that's what you're going to get.
Fix it myself.
I'm fixing myself, exactly. Yeah. And so what we did in the EPA, we turned around and said, look, let's try and do a publication that will be useful for non-statisticians. And what we did was we made a publication called she beat me to it. And what we did was we made a publication that you can download, and it's called Data Quality Assessment Statistical Tests for Practitioners.
I'll post it in the Dropbox folder for you.
And what we did was we elected to turn around and say, we will make all these tests just like as if you were baking a cake. All right? And that is, here is how it goes theoretically, step by step, and then immediately follow it by an example. Bang, bang, bang. And what we found is that's been a very useful thing, because nobody understands this at first blush. Look at this, H-O, what? I-H-O. And then, of course, your classical training steps in and says, oh, of course, null hypothesis, null is 0. So that's why it's H0. And alternative, well, that's why there's an A there. And then you say, but why is all these choices here? You see, depending on what your situation is, will depend on what your alternative is. Well, let's just see what it looks like in statistical language. There it all is. All pretty indigestible. All pretty indigestible. Let's see what is going to happen. Everything starts with the null hypothesis. That is key. That's your first step, and that is key to the problem. And then this null hypothesis is either rejected or not rejected. You say, oh, come on. Can't you just say rejected or accepted? Well, of course, all the theoreticians will come and say, oh, no. Oh, you've got to be so precise. If you say accept, you will probably mean accept without further thought. You say, no. You know? And then if you really want to upset people, you say, well, when would I never not reject the none hypothesis? You know? And it's only then that the statistician realizes that you're pulling his tail, right? And then sort of turns around and says, all right, okay. You can say you can reject or accept, but don't take it literally. This is very careful because of this last word. Look at what it says. The null hypothesis assumed to be true unless there is overwhelming evidence that it's not true. Can you think of an everyday, unfortunately, occurrence that this is part of our lives? How about in a courtroom? When you're hauled up in front there and you are accused, what does the judge say to you? You assume the person is innocent until there's presented overwhelming evidence that it can't be true. In other words, you're going to hang on to this null hypothesis like grim death, all right, until it just can't be true. Okay, let's see. Let's do a very simple one with very, very simple values. Do you see that there are 9 values here? See, there are 9 random samples. Is there evidence that the mean lead concentration from this site is greater than 100? Superficially, when you look at that data, does it look like the data is saying it's over 100?
Yeah.
Go on, guys.
Yeah.
Yeah. That one's under, that one's under, that one's under. But the rest of them are over. So initially then, would you say that we've got a problem? Problem in the sense that, is it easy to make a decision? Well, no, because there are values that are much less, right? Superficially, it looks like they're going to be over. But can we prove it's over? That's where we're going to deal with it. Here's our null hypothesis. We're going to take for our null hypothesis that the mean is less than or equal to 100. I know it says that some are bigger than 100, but we're going to try and prove that it's over 100. And what you might sort of consider scribbling on the side of your note there is that the thing that you want to prove, that goes into the alternative. And what do we want to prove here? Is this site greater than 100? Are we positive that it's greater? So what we're going to do then is turn around and say, the mean is less than 100, in other words, the site is okay. And the thing we want to prove, that it's bigger than 100, that goes in your alternative. So if you think as a rough rule of thumb, the thing you want to prove goes into the alternative, you can't go far wrong. There's your test statistic. You know, the t-test. There it all works out. Now, what is on the back of your example, the sheet that I gave out, was a set of t-tables. And if you look in the t-tables, you'll be able to pull out the number 1.86. Look for n minus 1. How many was n? There were 9 points. So you look at 8 degrees of freedom, 95%. You should get the number 1.86. And there's the conclusion. Since our test, our t-value was not bigger than that, we keep the null hypothesis. In other words, we have not proven that that site is bigger than 100. Yes, it looks like it's bigger than 100, but we can't definitively say that it's greater than 100. Supposing our test statistic had come out to be 2.22, what would we have said? Supposing it had come out to be 2.22, we would have compared that to the tabulated value, and because it's bigger, we would have rejected the null hypothesis, and we would have said then we have overwhelming evidence that it is bigger than 100. Was it obvious where these things come from? Well, not really. I mean, yes, they're straightforward, but sometimes you have to choose this for yourself. In this particular case, I said 95%. Does it have to be 95%? No, it could be 90, could be 80, depends on the situation. Interesting enough, what do the courts say? The courts have actually come round to say 95% seems to be a commonly accepted number. And so if you do things consistently at 95%, the courts will actually back you up. Good to know? Yeah, yeah. Only one yes? Doesn't anybody want to go for coffee?
Yeah.